All right, so let's take a look at what we've got going on in Unit 3. There's 4 chapters, so starting with Chapter 6. We talked about isopleths before, and isobars actually connect are on maps. They're lines on maps that connect locations with the same pressure. And then we said that actually kind of you see some from left to right, kind of the bullseye that we see on the pressure for the surface maps anyway for pressure. And so when you see the tight isobars, think strong wind, and we see those loose isobars, think weak wind, and we call that strong. Those tight isobars, we actually call that a strong pressure gradient versus a loose pressure gradient, or a strong or steep pressure gradient. How do we've talked a lot about pressure in this unit because actually difference in pressure creates wind. That's coming up here in a minute. But how do you measure pressure, or what units do you use? If you've been using their weather logs or doing a looking up everyday pressure for your weather logs or on the well, anyway, to the public it's usually inches, and actually that's inches of mercury. But for the weather maps, these isobars are in terms of millibars, and that's abbreviated MB. And then actually for your test, you're going to want to know that average sea level pressure in terms of millibars is 1,013 millibars. So yeah, the thing that creates wind in the first place is basically you have air that's crammed together and air that's not crammed together. So that's what we call a pressure gradient. And so the air is going to move from high pressure to low pressure. And that green line actually is what we call pressure gradient force. That's the push from a high to a low. Hydrostatic equilibrium, kind of down there, I've drawn the Earth's surface. And we have from you guys know that as you climb a mountain, the air gets thinner. So actually we have what we call a vertical pressure gradient force between air down here at the Earth's surface and air at upper elevation. So that's the purple line. And you would think then we'd have a vertical wind, right? But actually gravity is the thing that balances that out. And that balance between that vertical pressure gradient force and gravity actually is called hydrostatic equilibrium. Coriolis force, you're going to want to know some features about the Coriolis force. First off, it's created by the fact that the Earth is rotating on its axis. If the Earth weren't rotating, we wouldn't have this Coriolis force. It's strongest near the poles and basically zero at the equator. Coriolis force only works on large-scale fluids, and fluids could be water or air, or water or gas. And if those fluids are moving fast, the Coriolis force will deflect. It's an apparent deflection, so an apparent motion to the right in the northern hemisphere and to the left in the southern hemisphere. So those are kind of some general rules. And the last one is to compare those surface high and surface low pressures. We call those anticyclones and cyclones respectively. So around a high, an anticyclone, wind will go clockwise. Around a low, it's called a cyclone, wind will go counterclockwise. In the center of a high, actually the air is descending or moving down. And so, trying to change my timing. And so that descending air actually creates nice dry air. Around a central low, actually that air is ascending or rising. And one of the things we've talked about earlier is that rising air will expand and cool. And so actually you can oftentimes get cloudiness associated with those central lows, those cyclones. We talked about, actually in the next chapter, we're going to talk about those Rossby waves, right? And they have ridges and troughs, and they're kind of mapped out by the jet stream. But anyway, highs are associated with ridges, and lows are associated with troughs. And then just in general, and actually I kind of superimposed in purple at the top there, the highs generally have kind of loose isobars, which means not much wind, right? And the lows oftentimes have these tight isobars, steep pressure gradient, and with steep pressure gradients you get lots of wind. So if you're going to go ahead and turn this in for credit, I'm going to go ahead and give you I'm kind of giggling, I'm going to give you your first code, and your first code is Bob, B-O-B, okay? Okay, so there's another code word actually on the last page. Okay, so on to chapter 7. I brought in a figure of the three cells in each hemisphere that we talked about. The Hadley cell is closest to equator, and then in either hemisphere, then we have the Ferrel cell, and then both hemispheres, of course, we have a polar cell. And you can kind of think of them as divvying up kind of every 30 degrees. So we have 0 to 30 is the Hadley, 30 to 60 is the Ferrel, and 60 to 90 is the polar cell in both hemispheres. Kind of, right? So the doldrums, we said actually the doldrums are associated with actually the intertropical convergence zone. And I don't think the ITCZ, the intertropical convergence zone, is on this test. Is that crazy or what? As much as I love it, right? But the doldrums are associated with the hot spot. That's those kind of variable low winds. The polar front is actually between, remember, the Ferrel and the polar cell. And then we get to the winds, the surface winds. So they kind of alternate. Easterly trade winds associated with the Hadley cell, mid-latitude westerlies associated with the Ferrel cell. Actually, that's where we are. The polar easterlies associated with the polar cell. We have an equatorial low. Again, that's associated with, and I'll go ahead and just write that on here. It won't be on your other sheet. But the equatorial low associated with the intertropical convergence zone. And again, that's not a term that's on your test. Go figure. And then we have those semi-permanent highs associated with the subtropical high where the air is descending between the Hadley and the Ferrel cell. And then we have the polar high, and I think I got this a little, well, anyway, the polar high is actually at the poles at 90 degrees. Basically, air is descending there. Very good. Then we have surface winds here in the Midwest, or the mid-latitude westerlies, right? We're in the Ferrel cell, mid-latitude westerlies. Jet streams, I'll bring in a picture here. Actually, there's two jet streams, and they are both ribbons of fast-moving air, and they are between the cells. So the jet stream, the subtropical jet is between the Hadley and the Ferrel cell, and then we have the polar jet between the Ferrel and the polar cell. Okay, yeah, that should work. And so I have a question on the test that's going to ask you, upper level winds are westerly winds, and why is that? And then I'm going to remind you that at aloft, at upper elevations, actually over the equator we have a high pressure, and then over the poles we have a low pressure. And it has to do not with temperature, but kind of, well, with temperature at the surfaces, that the air is kind of squished down at the poles, so it makes an upper level low, and air is kind of still a little bit fluffy over the equator, so it makes an upper level high. So then actually that creates a pressure gradient force that is from the a pressure gradient force that is from the equator towards the poles. And so basically you would think that there'd be a wind that would move from the south to the north, from the equator to the poles, from the high to the low. But in the northern hemisphere, deflection's to the right. So basically what happens is we have that rightward deflection, and it makes our westerly wind. And remember that once it gets kind of between those isobars, it's just going to kind of stay in a groove. We call that geostrophic wind. Okay, so that's how that works. And my thing in green up there is that actually that this pressure gradient force will increase with elevation. And as the pressure gradient force increases, then also the winds will increase with elevation up to, as I understand it, the stratosphere. All right, Rossby waves. Actually, the next two kind of go together. So I'm drawing kind of a Rossby wave here. And actually, Rossby waves, you can have kind of this wave pattern in your, most notably in your jet streams. And then your winds kind of follow your jet streams. Your upper level winds follow your jet streams. And you can have I think your text said 3 to 5 kind of Rossby waves encircling the Earth at one time. But those Rossby waves actually are a meridional flow. Okay, the opposite of meridional flow is zonal flow, and in blue I put there zonal straight flow. So those Rossby waves have what we call ridges and troughs, And so ridges are, later on, we're going to say actually associated with, ridges are associated with, anticyclones, and troughs are associated with cyclones, highs and lows respectively. So let's see, I guess that's it. So meridional flow is wavy, and zonal flow is straight. So speaking of meridional flow, and I don't have anything to add to this, just simply that waviness actually, can you see where you can see it kind of goes up and down and up and down. As it goes up, it's transferring in the northern hemisphere warm air to the north, and as it goes down, it's transferring cold air to the south. Okay, so that waviness or meridional flow actually kind of helps equalize temperatures versus zonal flow, which does not. What creates ocean currents? Wind, quite frankly. So if we have these kind of prevailing wind patterns, wind circular patterns around the semi-permanent highs and the semi-permanent lows, actually that's what creates our currents. Our ocean currents. So the last one, El Nino versus La Nina, and we focus on the situation between kind of the west coast of South America and Australia or Indonesia, and that's what we call the Walker cell, kind of between those two. But anyway, if you look at that's in the Hadley cell, and if you look at the trade winds that are supposed to be easterly, during an El Nino year, actually those easterly trade winds will weaken or even peter out, which means actually they'll become, instead of an easterly trade wind, they'll become a westerly wind. And so actually this has consequences for something called upwelling, and I had to kind of explain what upwelling is. Upwelling is a normal deal where basically off the coast of South America off the west coast of South America, they count on cold water upwelling, kind of cold water moving up and bringing actually nutrients and cold temperatures. So during an El Nino, the upwelling actually is extinguished or lessened. Upwelling is lessened. And so actually in South America, they experience then warmer temperatures. And so if we compare that to La Nina and focus on what the trade winds do, actually during a La Nina years, the trade winds intensify, which means upwelling increases, which means that actually off the west coast of South America, they're actually even cooler. So what that does to the other end of the Walker cell, or over there in Australia, is during El Nino years in Australia, actually they're going to get less precipitation and the sea levels are going to drop. And during La Nina years in Australia, actually they would experience more precipitation and they can have sea levels rise. So on to Chapter 8, air masses. So what's constant within an air mass? The big things, quite notably, are in a chunk of air that we call an air mass. That air mass needs to have kind of similar temperature and moisture content. And we say actually the temperature and moisture content is at least the same for a given horizontal layer. So what makes a good source region? It needs to be relatively large, uniform, and it needs to be flat. It needs to be, a chunk of air needs to be able to kind of move after it sits there for a couple of weeks. Notice that, and actually I think this is on your test, what does not make a good source region in general is the middle of the United States. Not a good source region. So which air mass only forms in the summertime? That was the one over our southwest, the continental tropical air mass, only in the summertime. And down there at the bottom, I went ahead and wrote all 5 types of air masses. Continental Arctic, continental polar, continental tropical, maritime tropical, maritime polar. The first 3 are continental, so they're relatively dry. The last 2 are, the M stands for maritime, so actually they're moist. And then remember the second letter, is capitalized in designating the air masses. And the A stands for Arctic, bitterly cold. The P stands for polar, just simply cold. And the T stands for tropical. All right, and then the last topic here is lake effect snow. And so lake effect snow actually is a type of air mass modification. So the air mass that's being modified is cold and dry, and it goes over the Great Lakes, which is actually oozing. And remember, this kind of happens in the when we're transitioning from fall to winter. So it's still nice and warm, so it oozes water vapor. It loads up your dry air mass, so it turns into basically, instead of continental polar, maybe a maritime polar, okay? So basically it becomes saturated, and then on the downwind side of the lake, it can dump its snow, and that's called lake effect snow. And the last chapter is this one. And so sorry, kind of went on. In general, what a weather front is, it's the meeting of two air masses. There are 4 types of weather fronts that I want you to know, 4 main types of weather fronts. We have a cold front, a warm front, and a stationary front. Okay, and the thing about the cold front and the warm front is basically you in a cold front you have cold air moving down from the north, for us here in the northern hemisphere, and a warm front you have warm air that's coming from the south. And then a stationary front, basically it's a standoff. You have the air is not moving. You have cold air to the north, warm air to the south, and it's, well, not necessarily due north or due south, but on either side of the stationary front, I should say, you have warm and cold air, and they're not moving. The last one is an occluded front, and we use a purple line, and it is got notice that it basically, and we'll talk more about it here in a minute, but in an occluded front, it's purple and it has alternating semicircle, triangle, semicircle, triangle. And the cold air is basically outrunning the warm air in front of it. That's an occluded front. Actually, that's the next topic. Okay, so how does an occluded front form? Cold air is always faster than warmer air. So basically that cold air outruns the warm air in front of it, and it lifts that warm air up. And of course, with lifting, we know if there's some moisture, it can go ahead and expand and cool and begin condensing within that chunk of air. So I went ahead down here at the bottom and put a couple of figures for your warm front and cold front. And you should just generally know, for instance, if you have a warm front coming, you would expect the temperatures to get warmer. If you have a cold front that is going to come and get you, you're going to be colder. The other thing about these two fronts is they definitely have a difference in the type of precipitation you can expect. The precipitation associated with a warm front is calm and long-lasting. The precipitation associated with a cold front is intense and short. And so, of course, we have nimbostratus clouds giving us our precipitation with a warm front, and we have oftentimes cumulonimbus clouds giving us our or some sort of cumulus cloud associated with precipitation in a cold front. All right. So what makes those cold fronts potentially violent? One is that cold air is moving very fast, and the other is that basically that cold air is hugging the ground, and so it has a very abrupt, what we call transition zone, not much of a slope at all. Let's see, overrunning. Overrunning actually can be seen in the figure with your warm front. And overrunning, even though warm air is the aggressor, warm air is moving in on cold air, that cold air in front of it is hugging the ground. So overrunning is where the warm air goes up and over the cold air it's trying to replace. And anytime you get lifting like that, you can get clouds. And so overrunning, oftentimes you can see on a radar as far as the clouds being formed. Dry line is a clash between, it's like a fifth type of front, and it's clash between two warm air masses. One of them is moist and one of them is dry. So we have maritime tropical air mass and a continental tropical air mass meeting in a dry line. So the last one is mid-latitude cyclone, and just general, I brought a figure in from your textbook. And so know the kind of the three fronts, maybe even be able to draw this. Put it on your note card, mid-latitude cyclones and maturity. So we have the occluded front kind of around the low, and then kind of coming off the occluded front, we have the cold front and the warm front. Okay. Other things about a mid-latitude cyclone, aside from those three fronts, weather fronts, is that winds will be going around the central low. Oh, by the way, mid-latitude cyclones have a central low. And so around a central low, we know in the northern hemisphere, air is going to go counterclockwise. The other thing about mid-latitude cyclones is that they will generally follow the mid-latitude westerlies, so they go generally move west. Okay, and I guess the last thing is just note the kind of the shape of the clouds, and you can kind of see it looks like a two-tailed comma, okay, in this figure that I brought in. So if you're doing this for lab credit, the second, or not for lab credit, sorry, if you're doing this for review credit, the first word was Bob, and this word is gamma. Gamma. So those are your two code words to let me know that you watched this video.